Welcome everyone. My name is Rutu Joshi and I'm the session chair of this session. This session is titled Innovative Applications. Geosynthetics continue to serve an integral role in geotechnical and civil engineering applications. Innovations in geosynthetics, be it in manufacturing processes, use of new materials, development of novel products, or creative approaches in using geosynthetics, are critical in advancing their use to solve challenging problems of our time. As aptly said by Sir Ove Arup, a pivotal engineer of the 20th century, quote, engineering problems are underdefined. There are many solutions, good, bad, and indifferent. The art is to arrive at a good solution. This is a creative activity involving imagination, intuition, and deliberate choice, end quote. And innovation in geosynthetics is certainly a creative activity. The Geosynthetics Conference invites you to attend several engaging presentations in this session on innovative applications of geosynthetics by esteemed professionals in our field. A couple of things to note before we start the presentations. You will have the opportunity to ask questions during this on-demand session by clicking the questions button at the bottom of the video window. Your questions will be sent to the presenter to answer as soon as they are able to. To claim PDH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey for any sessions that you attend. Please note that you will need to include the verification code shown in this session to verify that you did attend this session and ensure that you received the proper credits. With that, please enjoy the presentations.
Good morning, good afternoon, or good evening, ladies and gentlemen, depending on from which part of the world you are and have joined this event to listen my presentation. Today, I would like to discuss a new prediction model for estimation of the deformation and punching shear resistance of geogrid reinforced working platforms, especially on their track plant. The dimensions and operating loads of construction machines are increasing rapidly. The main reason is that the large structural components and elements are being installed on construction sites. For example, for the case of wind turbines, 40 years ago, we were planning to install wind turbines with an average height of 15 meters. And only 10 years later, we decided to increase this height and to reach an average height of 50 meters. Today that we are talking, the hub height of the turbine is reached to 100 meters, and it's interesting to hear that the governments and accordingly the construction companies are planning to increase this hub height to 150 and 250 to 200 meters, and it's all in the case that the weak soil characteristics remain the same. This means that we need working platforms with higher strength and with higher capacity to withstand such large operating loads.
This brings us to the idea of application of geogrid reinforced working platforms, as you can see in the left figure, using which a very good and uniform distribution of stress and strain in soil will be achieved. And as a result, a surface deformation will be much less than the conventional working platforms, and a higher bearing capacity will be achieved on top of the working platform compared to only granular aggregates. The main reason is that the lateral movement of base course material will be restrained by application of geogrid material, and a very good distribution of stress will be achieved within the base course material.
It is very crucial to design the working platform package, including the thickness of the platform as well as the type of geogrids precisely in order to withstand the operating loads from the construction machine on site. Otherwise, an accident or failure which is unexpected may happen. Here we have collected some types of failures which are occurred over the time in the past. Some of them due to the very low distance of the construction machine from the edge of the platform, for example, the one in Asia, Brunei, or the other one because of very concentrated loads underneath the track, which cause a punching shear failure of the platform. Or it could be due to serviceability reasons because of very large deformation of the platform, which cause the tilting of the machine. So we have to learn lessons from the past and see which failures happens already and try to avoid them for future cases. And for a precise dimensioning or design of a working platform on site, we need to perform 3 important analyses. The first one is the punching shear failure of the working platform. And this is a failure which normally happens when the working platform is subject to very high compression loads. And this is a failure which is characterized by very large settlements and deformations of the working platform. There are different approaches in order to use it and are common. The most popular one is the BRE 470. This is not because of the accuracy of the model, it's because of the simplicity of the model and because of the wide range of application. You can use this model for cohesive soil and non-cohesive soil, but there are several weaknesses of the model that should be overcome in order to achieve a more accurate and safe design for punching shear failure of the working platform. The second analysis, which is normally neglected in practice, is the overall and rotational stability of the working platform, using which we are able to identify the potential failure surfaces over which the construction machine, the working platform, and the subgrade may slide. This is an important analysis, especially for the case when the subgrade is weak or when the construction machine is positioned very close to the edge of the platform, for example, 2 or 3 meter distance from the edge of the platform. The third analysis is related to the serviceability of the working platform, and using this analysis, we are able to estimate the deformation and differential settlements underneath the track of the platform, and accordingly see how much would be the maximum inclination of the construction machine and to control it. This is normally, for this purpose, we need complex numerical models or complicated analysis, and even sometimes finite element modeling may not help us because it doesn't consider the stabilization function of GeoGrid, which is related to the interaction of GeoGrid and aggregate. In general, there are several weaknesses in the current design procedure of working platforms that should be overcome in order to achieve a more reliable, economical, and in general, a better design procedure for working platforms. For example, the main important one is that the rotational failure of the working platform is neglected. However, as I mentioned in the previous slides, there are several cases in which the rotational failure of working platform becomes dominant. For example, when the construction machine is very close to the edge of the platform, or when the subsoil bearing capacity is not high. The second one is that the immediate deformation of the working platform, which may cause the inclination of the machine, is normally neglected because of the complexity of the analysis. And in general, the main important parameter, or let's say the only analysis which is considered for the design, is the shear failure of the platform. And even this analysis is dramatically simplified by some of the models. For example, the one in BRE 470, which considers the actual failure plan of the working platform to be a vertical plan, which is not realistic, or it considers that the tensile strength of the GeoGrid is only mobilized in a two-dimensional environment. And that's why in this study we have tried to overcome some of the weaknesses and to come up with a better and more reliable design process. With this background, we decided to improve the model from BRE 470, considering larger scale tests in Stuttgart. The test was set up for different arrangement of geogrids with no reinforcement, with one layer of reinforcement, with geocomposites, and with 2 layers of reinforcement in order to compare different cases with each other and to see how much is the effect of geogrid installation on the increasement of the bearing capacity of the working platform. There are loads with increasing magnitudes from 10 kilopascal to higher values are applied on the. Here we focused on the results related to reinforced and unreinforced platforms, and the results showed that the reinforcement will increase the bearing capacity and the allowable load on the platform moderately up to 25%, and accordingly the settlements related to reinforced platform is considerably lower than unreinforced platform. And besides, we have used the data from larger scale triaxial tests at Aachen University in order to investigate the mechanical properties of the soil and to see how the elasticity modulus and friction angle of the soil will be increased by application of 1 layer, 3 layers, and 5 layers of geogrid. So we use the shown methodology in order to develop a new model that can be used for design of working platforms, especially reinforced working platforms. In the first step, we focused on the results from the laboratory tests, as I shown in the previous slides, and using the experience from the tests and the experiments, we tried to modify the model from BRE based on the theory of Meyerhof and Hanna. And we did the modifications such as solving the equation in a in three-dimensional environment and mobilization of the geogrid tensile strength at the perimeter of the structure, perimeter of the track, and also by assumption of failure plan, which is more realistic compared to the plan which was assumed by BRE 470. And once the model was improved, we did the validation procedure, and then we set up kinematic element models and we compared the results of the model with the KIM models. And in the end, we performed a parameter study for different range of soil properties for weak soil, for soil with higher bearing capacity in order to validate the model for different conditions. On this slide, you can see the results of the validation of the hybrid model and a comparative study between hybrid model and BRE model for the parameter, which is called the allowable load on the working platform. And the allowable load is one time calculated by the model of the hybrid and also the other time by BRE model. And it has been measured also from the experiments. And the graph shows the relationship between the model, the value predicted by the model, and the value extracted from experiments. And in order to be on the safe side, we need to be under the line Q test equal to Q model. Otherwise, the model produces unsafe results. And the more we are close to the line, the more optimized is the model. And here you can see the result, and it can be concluded that the hybrid model produces more optimized and more economic results compared to the conventional BRE model. On this slide, you can see the results from the Aachen University test, and it has been shown that how the application of 1 layer, 3 layers, and 5 layers of geogrid will increase the mechanical properties of the soil. Here we have focused on the elasticity modulus of the soil because it's the most important parameter for the determination of the settlements and the deformation of the soil. And it has been shown that by application of laid and welded geogrids, it is possible to increase the soil elasticity modulus up to 70%. So the main objective of this study was to provide a knowledge base through performing large-scale laboratory tests and to improve the understanding of the interaction of geogrids and aggregates for the case of working platforms. And it was planned to provide a reliable methodological approach for the calculation of working platforms under large concentrated loads by overcoming the weaknesses from BRE model, and also to provide a relation for the calculation of immediate deformation of working platforms. The objectives are already achieved, and a new model is developed which can produce safe and reliable results. Thank you very much for your attention. Please do not hesitate to ask your questions.
Hello and welcome to my presentation on high-strength polymeric geocell reinforced railway line repair in degraded permafrost condition. I'm Sanat Pokhrel, Principal Engineer at Stratum Logics, and my co-author is Mark Bro. He is the President of Paradox Access Solutions, both from Atchison, Alberta in Canada. Before proceeding to the details of my presentation, I would like to thank the engineers and construction crew for their hard work in extremely harsh weather condition and all the other people that made this project a success. Today in my presentation, I will talk about repair and rehabilitation of a flood damaged railway track using polymeric geocell structure in Manitoba, Canada. I'll talk about project background, issues, designing with geocells, construction, and conclude. The project is the railway line between Gillam and Churchill in Manitoba. Churchill is a port city in northern Manitoba at the mouth of Churchill River on the shore of Hudson Bay. The nearest roadhead is the village of Gillam, approximately 300 kilometers south of Churchill. The length of the track under the consideration is shown with a thick line along the railway line, as the major damage area in the photo shown on the right side. Built in the early 1900s and operational until 2017, spring, the rail track crosses several stretches of permafrost. It is the only mode of land transport to Churchill. Lateral spreading of expensive ballast and subballast material and permafrost degradation had impeded the smoothness of the rail ride. After a site visit in May 2016, polymeric geocell reinforcement to improve the track condition and to protect the subgrade was recommended. Flood in 2017 spring rendered the track unusable and exposed permafrost at several locations. These pictures were taken during the site visit in May 2016. It shows the condition of the rail track. The picture on the left side clearly shows the poor riding condition of the rail track with uneven settlement. Picture on right shows previously installed thermosiphons, but the site visit could not confirm whether they were operational. The flood of 2017 spring that was triggered by melting snow and rain caused damage to the underlying permafrost as well. There were 26 locations needed immediate repair work in the damaged stage of the track. Out of that, 12 locations had washout length up to 210 meters and others were shorter than 70 meters. These locations also needed new culverts for stream crossing. The repair work with polymeric geocell included installing culverts, erosion control, geocell reinforced embankment to support dynamic load from the terrain. In this slide, you see two sets of pictures. In the top two pictures, you can see pictures of flood damage during the flood in the spring of 2017 and the extent of the damage when the flood water receded. Pictures taken before the construction in 2018 are the bottom two. You can clearly see the extent of damage. Issues on the railway track. There were severe problem of lateral spreading of the ballast and subballast material, erosion of the embankment material at the side slopes, washout culverts, and need for culverts at the couple of new locations, exposed degraded permafrost at the washed out locations, harsh winter, shorter construction season and linear construction sequence, and limited available budget. Even daily commute for the construction crew from the nearest available camp in Gillam on high rail or caboose was not easy. The travel time alone was in the order of 6 hours two-way per day. Understanding the sustainability requirement, a design solution was proposed. A high-strength and highly creep-resistant noble polymeric alloy geocell was chosen as a reliable option to improve structural strength, provide confinement and erosion control benefits to counter these issues. Geocell expedited the work and reduced the budget as the washed-out waste material was reused. The design was proposed to provide necessary structural strength for railway traffic, protect the underlying permafrost from the further degradation, provide erosion control at the embankment slopes, facilitate linear construction schedule, complete the job in an available time and budget significantly less than the estimated for conventional construction, control the lateral spreading of the subballast material. In next two slides, I will talk about geocells. The first, the geocell in load support application. It provides lateral and vertical confinement, stiffer layer to distribute loads over a wider area, reduces stress on the subgrade, thicker reinforced zone, and creates a beam and slab effect. The pressure bulb on right is when it is reinforced, and when the pressure bulb shown on the left side is when unreinforced case. It is developed from Pochrel 2010. Use of polymeric alloy geocells. Geocell is a proven technology since 1970s, developed originally by US Army Corps of Engineers. High-strength polymeric alloy geocell are recent addition. Design methods are available after rigorous research conducted at various institutions all over the world. NPA geocells have design methods verified by researchers in Canada with understanding the performance in load support application. Design basis for this project. ARIMA and CN railway design principles were checked. Slab effect by geocells to protect the weaker region within the permafrost was anticipated with the wider load distribution. Only 5% of the applied stress on the top was transferred to the subgrade. Boussinesq's method on stress distribution and stress reduction by geocell were used to calculate the stress transferred to the underlying layers. The design used a modulus improvement factor of 3.5 to 4 by geocells. In the design, height of geocell plus 25 mm was assumed as the reinforced thickness as recommended by Pochrel 2010. There were very limited information available for design. Aerial visual survey and photo taken from helicopter, a photo of damaged sections from site visit by a person with GoPro, the size of previously existing culverts from HVR records. Due to accessibility issues, some design decisions were made during the construction as to reach the next location. The first location was to be completed. As there were no facility to compaction, a 4-ton roller was used. 12.5 millimeter under the roller was taken as maximum rut and used a minimum pass of 12 passes. This slide shows the typical design sections that was used for the construction. The drawing on right side shows a double layer structure where the permafrost was also damaged and there were exposed surface of permafrost. On the left side where the permafrost was not damaged and only the washout had happened on top, there was single layer design as shown in the drawings. Material used in construction. Ballast material required amount hauled in from Gillam, which is 200 kilometer far on the south side. Subballast, reuse of washed out granular material available at the location, and when extra material was required, it was brought from Gillam, that was 75 millimeter minus P-ton sandy gravel. Geotextile 890 Newton woven geotextile and non-woven geotextiles 911 Newton and 1330 Newton were used. Nanopolymeric alloy geocells were used with the height of 150 millimeter and 330 millimeter between the weld seams. Type C and Type D, two types were used. Type C had 19 kilonewton per meter strength and Type D had 22 kilonewton per meter. The next two slides will show the pictures during construction. Track removal and geocell installation is in this slide. The top two is the track removal and the repair work. The bottom two shows the geocell installation and compaction at below the subballast layer. In this slide, the top two pictures show the installation of geocells for subballast layer, that is type D geocell, and the installation of ties and rail. The bottom two pictures show the completed sections. Let us do a discussion on the design. The design gave due consideration to structural requirement and environment, protecting permafrost, controlling tag degradation, erosion at the embankment slide, strengthening the subballast structure. The use of available aggregate from the washed out location reduced about 50% of the virgin aggregate extraction. These saving by use of geocell saved hauling more than 200 kilometers, resulting in huge reduction of carbon emission. The project was completed in effective 3 working days at a cost of about 20% of the initially anticipated for conventional rehabilitation work. The construction equipment available was limited, so a coordinated approach between the geocell installers, culvert pipe installers, and earthwork crew was of utmost importance on getting the job done in a timely manner. It was very coordinated, otherwise in that harsh climate, it would not have been possible to complete that in 33 working days. This is the day we were all waiting for. Train arrives in Churchill in 2 years. Work completed just when daytime temperatures started falling sub-zero. Access granted on 31st October 2018 after approval of Transportation Safety Board of Canada. This railway is in operation for more than 2 seasons without any known issues of operation. Before jumping into the conclusions, it is important to see how the things turn up for this project. We were called in to improve the railway line just for the riding conditions. There was no smooth. They wanted to run the railway on 50 kilometers per hour. We recommended using geocells, but it didn't happen. The flood came and then it damaged, and completely railway was damaged. Then we said like these solutions can be done in quickly, but it took almost 2 years to convince that geocell is the better solution and it works. The conclusions is the NPA geocell reinforced design of the railway embankment proved to be a successful solution for maintaining and strengthening the railway structure. Geocell reduced the carbon footprint by reducing the amount of material required and reusing the available material, washed out material at the site. Geocell helped in controlling lateral spreading of the poorly graded sandy peat run gravel subballast, control the settlement and damage of the permafrost, control the embankment side erosion. The design saved both the construction time and budget, proved a perfect solution in a linear construction project. This design is a viable method for the future similar infrastructure in the permafrost and other similar areas. One thing to think here is we wanted to reinforce the ballast with the geocell too, because that would have strengthened the ballast and lateral spreading would have minimized. But the problem was the tampers. Tampers would have damaged geocell, so that we couldn't do it. If we had used geocell, we'd have to use 3 inches more material. That's why we said we didn't use geocell reinforced ballast. I would like to thank all of you for listening to me. I have just showed a case where geocell was the best option. I would like to also thank Can-Do Construction for their part in construction and Clifton Associates for construction and supervision and information. I would also like to thank the city of Churchill, where I had the opportunity to go and talk to them about regarding this project. Thank you, everyone. Bye.
Hello, my name is Brian Fraser with Layfield Geosynthetics, and I'm based out of Edmonton, Alberta, Canada. This presentation is on geosynthetic portable cofferdams for civil construction applications. And I'd like to also acknowledge my co-author, Mike Neal from Layfield USA, based out of Eugene, Oregon. And this picture shows an example of a geosynthetic cofferdam as part of some bridge foundation construction work. It's actually 2 dams, and the dam closest to us in the picture is a 10-foot dam, and backing it behind it is an 8-foot diameter geosynthetic cofferdam. And this cofferdam project is in Baytown, Texas. Cofferdam systems have been used for many years in civil construction waterway applications. These have included steel pile cofferdam systems, earthen cofferdams, as well as rock-filled cofferdam systems. And for about the past 20 years, we have been increasingly seeing the use of geosynthetic modular cofferdams. And this picture is actually a good example showing the installation of a 6-foot diameter geosynthetic cofferdam in a section of the Eagle River in Colorado. And this was part of some shoreline construction activities. Cofferdams are used as temporary barriers in or near a water source to help allow dewatering, diversion, or damming of water. They actually partition off or hold back water, helping to create a dry area, allowing a project to work on time and safely. There's temporary cofferdams versus permanent dams, typically concrete dam systems. And there's different materials used in cofferdams: earthen dams, rock-filled, steel, timber, and concrete. And various different cofferdam systems. There's cantilever steel pile dams, steel brace dams, earth embankments, double wall, and cellular cofferdam systems. And as mentioned, increasingly we're seeing the use of modular or portable geosynthetic cofferdams. And there's different applications for geosynthetic cofferdams. The main applications are dewatering, diversion, damming, and flood control. Specific applications include new bridge construction and for repair work to existing foundations. They're also used extensively for pipeline crossings, including new pipeline work and pipeline repair and maintenance, irrigation canals, river crossings and diversions, as well as just overall shoreline civil construction applications are common uses for geosynthetic cofferdams. And the picture on the right shows a unique project in northern Alberta. It's a double cofferdam system. Upstream, you see the white cofferdams. Downstream, you see the black cofferdams. And in between is a steel flume allowing water to flow in between, while equipment is being used for construction and dewatering activities. And this picture shows an 8-foot diameter geosynthetic cofferdam installed in the Green River in Washington State. We're actually using pumps onshore to divert water around the dams while we dewater this site to support construction activities downstream. And there are different geosynthetic cofferdam systems available in the marketplace. Specifically, our geosynthetic cofferdam is made with 2 NSF grade impermeable water-filled inner tubes, and they're normally filled with the local water source on site. And these inner tubes are protected with a high-strength geotextile odor wrap material. To connect the dams on site, we have special connection collars, and each dam comes with a fill and drain port system. The system is also available with a patented center baffle curtain, which helps to prevent tipping and movement of the dam. And the dams are available in different sizes, from 4 feet to 16 feet in diameter, or 1.2 meters to 4.88 meters, as well as standard lengths are available from 100 feet to 200 feet, or 30 meters to 60 meters. And we will custom produce dam lengths based around project size requirements. And all components of the geosynthetic cofferdam are prefabricated in our factory. And all geosynthetic cofferdams need to be properly engineered and designed. Systems need to be designed to withstand hydraulic forces and loads, including the coefficient of friction of the bottom of the dam and the subgrade application. Hydrodynamic loads need to be determined for tipping, sliding, and overturning of the dams. And internal structural calculations on the materials are required to ensure the materials meet the mechanical stresses and loads. And of course, adequate safety factors must be built into the design. And the drawing on the right shows the typical lateral forces of water and how they impact the design application. And there's numerous advantages to geosynthetic cofferdams. They're normally very lightweight in their design and come prefabricated and ready for rapid deployment. They're also modular in their design, coming with different types of connection systems or collars. They're also very flexible, can handle bends and turns and different configurations of site conditions. And they provide far less environmental impact. They're easier and quicker to install as well as remove. And they're very economical compared to other structural cofferdam systems. And they can also be used to store water temporarily on site for different types of remediation and cleanup applications. And the picture on the right just shows the flexibility of portable cofferdams and how they can be configured to your specific site conditions. There's a number of risks and challenges to installing geosynthetic cofferdams. One of the main challenges is trying to do installations in moving water, and certainly fast-moving water. Projects need to be designed to calculate hydraulic forces of these water flows. We also need to be concerned with deep water installations and need to know the water depth at all times. Potential punctures from debris in fast-moving waters can also be concerned. And it's also very challenging doing installations around ocean tidal forces. And in terms of flood control levels, we must know peak flood levels. We also need to know subgrade conditions and site access conditions. And of course, at all times, we need to be concerned with employee safety. And to address the various installation challenges, we require proper risk mitigation measures be undertaken. This includes proper site risk assessment for each project. We need to know the water body type. Are we dealing with a stream, river, lake, or ocean? And we need to know the water depth and flow rates, and based on historical depths and flow rates. We need to know tidal conditions. We need to know ground surface conditions, what type of site access we have, and whether or not we have site security. This picture shows a very unique recent project we did for Killisut Harbor in Washington State. This was done in 2019, working with the North Olympic Salmon Coalition and Washington State DOT. They needed to restore historical tide channels as part of a fish run between southern Killisut Harbor and Oak Harbor in Jefferson County, Washington. The overall scope of the Killisut Harbor project included the general contractor needing to build a new bridge and causeway in conjunction with working with the Washington State DOT. This required an extensive channel and dewatering excavation. Our scope included supplying and installing 1,400 lineal feet or 427 meters of portable cofferdams. And these needed to be done in multiple sizes, including 4-foot, 6-foot, 8-foot, and 12-foot sizes, or 1.2 meters to 3.7 meters. It was a fall installation, and we had to work around a protected wetlands site. The Killisut Harbor project faced a number of unique challenges. First and foremost, being a very environmentally sensitive region and the strict conditions to protect the salmon fish stocks and migration. It was an overall wetlands area which strictly limited the use of heavy equipment and site access conditions. We actually had to install the geosynthetic cofferdams by hand. We also had to work around tidal conditions, installing the cofferdams during low tide cycles only. Project also had strict monitoring and controls in place for silt and sediment release. And based on the fluctuation of water levels, we had to work with the 4 different sizes of dams, making it very difficult to do the connections. The installation of the 1,400 lineal feet of geosynthetic cofferdam took 7 days to install. We had a 5-person crew on site, and the contractor also provided some labor. Contractors stated they saved significant project time and cost with the geosynthetic cofferdams versus using a vacuum dredge system. There was far less environmental impact and disturbance, and all stakeholders appeared to be very happy with the performance of the geosynthetic dams. And this picture shows a great aerial view of the overall project. You can see the causeway under construction in the back. You can see the wetlands area, the channel that was constructed, and you can see the installation of the 1,400 lineal feet of portable geosynthetic cofferdam that was used for dewatering and silt control. On behalf of the IFAI and Geosynthetics 2021, I would like to thank everybody for the opportunity to present today on geosynthetic portable cofferdams in civil construction applications. I'd also like to thank my co-author Mike Neal from Layfield USA for his support, as well as recognize the contribution made by Robert Emmons from Layfield USA. Robert is a business development manager and provided much of the background on the Killisot project. My name is Brian Fraser, Vice President of Layfield Geosynthetics, and I can be reached at brian.fraser@layfieldgroup.com, and I certainly would be available at any time to answer any questions you had on this paper. Thank you very much.